Decision trees for big data analytics. Preface. Content of this lecture. In this lecture, we will discuss decision trees for big data analytics. We will also cover a case study of a medical application using decision trees in Spark ML. Before that, let us understand about the basics of decision trees. So, decision tree is a tree which is nothing but an acyclic graph which has the root node and other nodes. This is called the root node of a tree, and these are all called internal nodes of a tree, and this is called the leaf. So, the square boxes represents the node which is called a leaf node. In the decision tree, the predictions are there at the leaf nodes. And the internal nodes and the root nodes, they are called the decision nodes. Now, given a data set, we are going to construct this particular decision tree using the decision tree algorithm, and traversing the tree we can predict for a given query. So, whenever a new data set we get, we will be able to handle this particular data set for doing the predictions. So, details we are going to see in the discussion, and then how this decision tree is going to be useful for doing the big data analytics also we will cover through an example. Let us see a simple data set. And let us see what kind of predictions this decision tree will be able to make. So, to understand in a very simple manner, let us consider this data set as a query. So, the query is that we want to predict if Sachin will play the cricket or not. To answer this particular query, that means to get the prediction whether Sachin will play the cricket or not, we have observed the details of Sachin playing and also the weather conditions over 15 days. So, day 1 to day 14 over 14 days. Wherein we have considered that what is the outlook of the weather, if it is sunny, overcast, raining, and the humidity of every day, that is whether it is high, normal, or the wind speed, whether it is weak or is strong. And we have also seen that in these conditions whether that player Sachin has played or not. So, on day 1 it has not played, he has not played. Day 3 he has played when the weather outlook was overcast, humidity was high, and wind was weak, and so on. So, we have observed the 14 days of these different parameters, and also we have seen whether the player Sachin has played under these conditions or not. Now, using this particular data set, can we predict whether Sachin will play to the days which are a new day or a next day or not? So, decision tree, let us see how it is going to be useful. So, consider this data set, and our task is to predict if the Sachin is going to play the cricket on a given day. So we have observed the game playing of Sachin over a number of days. In this example, we have monitored or we have observed 14 days and recorded various conditions that might influence his decision to play the cricket. So under different weather conditions. So is it sunny or is it raining or it is having humidity, and then in that case, or it is having a normal windy temperature, what conditions are required and necessary and to predict whether Sachin will play or not. Even for this small or a simple data set, this becomes quite complex. So let us see how we are going to simplify using decision tree for this particular purpose. Now one thing is that this particular data set is basically observation of the last 14 days, so that becomes the training set, and using these examples can be predict this particular decision of a Sachin whether he will play the game or not. So that means the query will be that on day 15th, if outlook is raining, humidity is high and wind is weak, whether Sachin will play or not. So from this data set also it seems that it's not easy to get or understand this entire data set and come out with a decision to predict or not. But let us understand this particular data set, because decision tree is the technique which will understand these different parts of the data set or the behavior of that player Sachin, it will understand, and based on that it will do the predictions. So on day 15th, if it is raining and the humidity is high and the wind speed is not windy, slow or a weak wind is capacity, then whether Sachin is going to play or not. And by looking to this particular data and this kind, it will become very hard to decide the right kind of predictions, whether Sachin is playing in other days on one of these parameters and how this kind of condition, whether he will be playing or not. It's very difficult to predict. Let us see how in decision tree we are going to do this kind of predictions. So as we have seen, it is very hard to guess whether Sachin will play on day 15th, and but for this we have to understand when Sachin plays, what are the conditions when Sachin will when Sachin is playing. So there are 19 different samples when Sachin has played and under different conditions, 9, and these 9 different conditions when Sachin has played is required as the training to understand when he has played, and there are 5 different conditions when he has not played in those weather conditions. Now we will to understand this behavior of a player Sachin out of this data set, which is an observation of last 14 days. We can do this by splitting into the subsets of different classes, and then we can extract this information, and the decision information we can then basically use this information for predicting a new data set. So let us understand more details of this entire data set which is given. So if we classify this data set based on the outlook parameter, then there are 3 different outlook conditions. One is sunny, then overcast and raining, and these subsets which we are going to get in these different conditions. So we basically have obtained 3 different subsets. Now out of these 3 different subsets, we see that in when the outlook is overcast, we can see that here there are 4 different entries or 4 different days are there when this becomes yes, and there is no entry which is having 0 no's. So hence this kind of subset is called a pure subset which has all yes. When the outlook is sunny, then we can see this particular subset which has 3 no's and 2 yes. So this kind of subset is called impure subset. That means it is mixed, whether two are saying yes when the outlook is sunny, then Sachin has played in two of these conditions when the humid is normal and the wind is weak or strong, and in 3 different cases he hasn't played. So this kind of subset is called impure subset. Similarly, when the outlook is rain, then there are 3 different cases when Sachin has played and 2 different cases when Sachin has not played. So hence this becomes an impure subset. Now we can further split these impure subsets, and pure subsets need not to be splitted further. So now we can see that we can split, so that now we have splitted this outlook sunny based on the humidity, when the humidity is high or normal. So what we can see here, that when the humidity is high, all 3 cases the Sachin has not played. So 4 no's and 0 yes. Hence this is called a pure subset. Whereas when the humidity is normal, then there are 2 different in this subset, that means 2 yes is there and there is no 0 no's. Hence this is also called a pure subset. So when it is a pure subset, then decision can be easily made. For example, when the outlook is sunny and the humidity is normal, then Sachin has always played. So whenever a data of this category comes, we can decide about this. So here also, when under this split humidity, we have obtained both the pure subsets out of this split of sunny. Now then, let us see the rain. When the outlook is rain, then it has basically a mixed or impure subset which can be splitted further. So if we split further on this wind, what we obtain is that when the outlook is rain and the wind is weak, then we have got 3 different subsets. In this subset, the 3 yes is there, 3 times it has played, and 0 times he has not played. So this is also called a pure subset. Now as far as when the wind is strong, then we have obtained a subset where the 0 yes is there and 2 no's are there, and this is also called pure subsets. Now there is no further division or split required, and we have constructed a decision tree of this use case. Now if we summarize this particular decision, that decision tree which is constructed out of that data set, we have obtained that if when the humidity is normal and when outlook is sunny, then always that player Sachin has played. When the outlook is overcast, then Sachin has played, and when the wind is weak and the outlook is rain, then also Sachin has played. So there are 3 different cases when Sachin has played, and which is shown over here. In all other cases, Sachin has not played. Now not only this particular decision tree has yes and no cases, but it also has how many cases which are having yes. So, it will add to the confidence on this particular decision using these parameters. So, let us see the query which was given to us on day 15th, that if the outlook is rain and humidity is high and wind is weak. When the outlook is rain and the wind is weak, obviously it is going to play in this particular case. So, we are going to say yes. Hence, the decision is yes in this particular case using the traversing of the decision tree. So, by traversing the decision tree, we can predict that Sachin will play. And the confidence with which we are going to predict is 3/0. So, that means with the high confidence this particular prediction can be made. Now, as far as the decision trees are concerned, we are going to discuss one such algorithm which is called ID3 algorithm for decision tree. So, this algorithm was invented by Ross Quinlan, used to generate the decision tree from the data set. ID3 is the precursor to C4.5 algorithm and is typically used in the machine learning domain. So, let us see how the split of a node is done in ID3. Now, let us consider A, which is assigned to the best attribute for the splitting, and the decision attribute for this particular node is assigned from A. For each value of A, let us create a new child node. Now, split the training examples to the child node, and for each child node or a subset, if the subset is pure, then stop splitting further, else we have to split the node child into the subsets further. Now, Ross Quinlan, which has given this ID3 in 1986 and also C4.5 in 1993, and Brinmantel has given CART in 1984 from statistics about this decision tree algorithm. Now, the question is which attribute to split on. So, let us see that we have seen that there are 3 different attributes in that data set. So, which one we are going to use to split the attributes on that particular question is going to be that is the split decision. Which attribute to split on is a decision which we are going to see how decision tree is taking here in this case. Now, here let us see that it wants to measure the purity of the split, and this is the way it is going to take the decision of which attribute to split on. So, based on the purity of the split, the decision is to be evaluated. So, more certain about yes or no after the split. So, for example, if we have a pure set where 4 yes is there and 0 no's are there, then we can say with 100% certainty that this is a pure set, and the decision is very certain. Similarly, if the set is impure where 3 yes is there and 3 no's are there, then the decision which we are going to take is having completely uncertain, that is 50% chance of making the decision correct is there. So, this way we are going to measure using how many yes is there whether the set is pure or impure, and this is going to be the measure to go for the split. Now, so this particular must be the use of this probability must be the symmetric, that is 4 yes and 0 no's as pure, as 0 yes and 4 no's. So that means whether it is all yes or whether it is all no's, both are called pure subsets, wherein the decision is 100% certain to be correct. Whereas if the set is impure, then it is uncertain that the decision is correct. So we are going to evaluate this measure of purity to split on. Now, this decision tree uses different measures for making the decision whether to split or not. One such way is called entropy, that we are going to discuss. How using entropy we can decide whether to split further or to not to split. So entropy is represented by Hs here, and there are two variables, let us say p plus and p minus. So that is minus p plus log to the base 2 p plus minus p minus log to the base p minus, and this is nothing but the number of bits. So if we calculate the entropy of a particular set of training examples, then we will get the bits. So this interpretation of the bits we are going to use to infer whether to split or not. How this is all done, we are going to see now. Now, p plus and p minus percentage of the positive and negative examples in S we are going to evaluate. Now, interpretation is, let us assume an item X belongs to a set S, and we have to ensure or basically estimate how many bits are needed to tell if X is positive or the negative. So, for example, if it is impure set of 3 yes and 3 no's, then if we calculate the entropy of this impure set S, then it comes out to be 1 bit. So, 1 bit, if it is the entropy is 1 bit, then it is highly uncertain for the decision whether it is yes or no. So, the number of bits which basically will represent it, here it is 1. So, 1 means it is highly uncertain in this particular case. Now, if it is a pure set, let us here if it is 4 yes and 0 no's, and we want to find out the entropy of that set. So, entropy will be 0 in this case. So, if the set is pure, the entropy will be 0 bits. So, 0 bits means the decision is very certain, and if it is uncertain, that is highly uncertain, then the bit will be 1. Now, and rest of the decisions are in between 0 and 1. That is what we have seen. Now, so this particular diagram shows that if the number of bits is 1, if the number of bit is 1, here in this case, if it is, so if it is 1, then the decision will be half, 50% chance that the decision is going to be correct, 50% chance. So, it will be a 50-50, that means 50-50, and if all are positive or all are negative, then the number of bits which is required is 0 here in this case. For example, here in the pure set all are yes and 0 are no's. Similarly, another pure set when all are yes, all are no's and 0 yes, then also it is a pure set. In both the cases, the number of bits here, this represents the number of bits. In both the cases, the number of bits are 0. Hence, this is going to be a pure set, and this is also going to be a pure set. And this is the impure set condition. And so basically, either it is pure set, then it will take 0 bits, or it is highly uncertain, then it will take 1 bit. Whereas all other conditions are lying on either on the left side or on the right side, where the number of bits is varying between 1 to 0.5. So with this, we have understood that entropy can be useful to estimate whether whether we can go for the split or not. So if it is a pure set, then entropy, the size of the entropy is 0. That means we are not going to split. If it is highly uncertain, that is 50% are saying yes and 50% are saying no, then the value of entropy will become half. So the entropy will become 1, that is highly uncertain. And all other in between which are lying in between, so their values are between 0 and 1, that we have seen in the previous example. So we are going to evaluate this purity of the set using entropy to decide the split of the nodes. Let us see how this decision tree has used this concept. This concept is termed as information gain. So we want to see how many items are there in that pure set, and how many, and this particular expectation will drop after the split in that entropy value, and this can be termed as the gain, and that is called information gain. So information gain will be HS minus the summation of HSB, and that is the summation of all the values of A, and the set of all samples divided by that means subsets of all the samples divided by the set of all examples. Let us see how with this information gain we are going to do this kind of decision whether to split or not. So let us see here in this case of the wind, wherein the wind we have seen that there are 9 yes and 5 no's. So the positive variable is 9, which will be fed, and the total number of samples are 14. So minus 9 divided by 14 log to the base 9 divided by 14 minus 5 are no, 5 are negative. So 5 divided by 14 log to the base 5 divided by 14, that comes out to be 0.94. So information gain is 0.94 here in the wind. How about calculating this same information gain for weak and for the strong? For the weak we obtain 0.81, and for strong we are obtain 1. Now we can see what is the information gain here in this case of wind, whether we can split or not. So HS is basically the information gain of a wind, so that is 0.94, and this particular then for the weak case it is 0.81, and it will be divided by 8 upon 14. So, so total number of samples, if we count here, they are 14. So that total number of 14, and out of 14 we are for weak case we are taking only 8, 6 to 8, 8 divided by 14, and minus this comes out to be 6 divided by 14, and if we evaluate, the gain comes out to be 0.049 information gain. So if we split, then the net gain will be the positive gain of 0.049. Hence, it is better to split. So this way, using information gain, we can estimate, or the decision tree will make the decision whether to split or not. Now let us see how to grow, how to build this particular decision tree. So the trees is built greedily from top to the bottom, and each split is selected to maximize the information gain. So what we have seen here is that in the previous example, that after the split the gain is positive, so we have to maximize after the split, hence we are going to split in this particular case. So we can see here by this way we can find out the splits, and we have already seen that if we can do this kind of predictions to find out this whether to split a node or not. So whenever there will be information gain, and to maximize the gain, according to that maximizing the information gain, this particular splitting is to be done. So we have to find out the best split, and we have to do the decision based on that. Now there is another criteria which is called a stopping criteria, that the growth of the spanning tree or the building of the spanning tree, it has to be stopped. So the node depth is equal to the maximum depth of the training parameter, and no split candidate lead to an information gain greater than minimum information gain, and no candidate produces the child which have at least the minimum instances per node, training instances. So in summary, what we have seen in the decision tree is that here the automatic handling of interactions of the features is done, and computational scalability also we have seen, and interpretability aspects also. Now let us see how to build a tree using MapReduce. So now MapReduce will be applied for the decision tree algorithm, and here we will see the approach, and we will see more detail of it, how this MapReduce will be applied in the decision tree, so that the big data analytics can be performed with the help of this parallel decision tree implementation. Now here we are given a large data sets, and which has a lot of attributes. The size of the data set is also big, and the number of attributes are also more, and we want to build a decision tree. That is what is called the big data applying, that is the big data analysis. So here we have to see is that the tree, although data is very big, but the tree is small, and it can be stay in the memory, and maximum levels of that particular tree which is extracted out of big data is out of the 10 levels, and also we have to keep the data set, a very large data set, into the memory, and this data set is too big to be kept in one machine. So basically MapReduce we are going to use, which is going to compute over the cluster of machines. Now here in this particular technique, which is called the decision tree, we have to find out the splits, and then we have to find out which attribute along with which we are going to build the tree, that is the single tree which we are going to build. So we have to first find out which is the best variable around which the split has to be done or the tree has to be constructed. So the best, we have to find out the best attribute for the split to grow the decision tree. So after having identified a particular attribute, now we have to identify how the best split is to be done, so that in the left side and the right side of the tree can basically grow and so on. So these particular growth of the spanning of the decision tree, which we are going to see a level wise growth of the tree, and also the stopping criteria when we have to stop further growth of the tree. So this particular decision is called when we are going to split. So this is called whether the node, what is the condition in which we are going to split the node along, whether to split or not, and if it is, then which particular attribute will be the best to split. So all these things we are going to discuss, which are going to be implemented using MapReduce. So MapReduce, we have already seen that it is the input data set is now divided into the chunks, and these chunks are given to the mapper functions, and the mapper function will generate the key value pair, which is further given to the reduce functions, and they will generate the output. Now this particular implementation of a MapReduce for decision tree is published in a paper which is called Planet by the Google. So parallel learner for assembling numerous ensemble trees, which we are going to see here as the MapReduce implementation of a decision tree. So this is nothing but a sequence of MapReduce job that will build the decision trees, and here we assume that the values which are given in the data set, they are basically hundreds of numerical attributes, and we are going to build the binary tree, which is the decision tree, which is a binary tree, and this particular tree, which we assume that is small enough to be for each mapper to be kept in the memory, and data is too large. Let us see the different constituents in this architecture. So here we see that there will be a master node, and this particular master node in turn will decide about finding the best split and also the in-memory growth of the tree at the mapper end. And the intermediate results are also stored, and this all happens in the coordination of the master. So the tree is built level wise using these different MapReduce sequence of MapReduce operations. MapReduce operations are being coordinated by the master. There will be a master, and which will decide the best split, and also it has to decide about in-memory growing of the decision tree at the mapper. So let us see the Planet overview. So here in this particular method, we build the tree level by level, and one MapReduce step will build one level of a tree. So if there is a 10 levels, so 10 different MapReduce in sequence has to execute. As far as the mapper is concerned, mapper will consider the number of possible splits on the subset of the data, and this comprises of xi, v, and for each split it stores the partial statistics. Partial split statistics is then sent to the reducers. Reducers will collect all the partial statistics and determines the best split, and master grows the tree for one more level. So here the mapper loads the model and information about the attribute splits to consider. So each mapper sees a subset of the data D star, and the mapper drops each data point to find the appropriate leaf node L, and for each node L it keeps the statistics about the data reaching L and the data in the left and right subtree under the split S. So this way so each mapper will now has to deal with a particular level of the nodes and has to decide whether it has to be further split or not. If it is to be splitted further, then another iteration will go on with the next set of MapReduce job. A reducer aggregates the statistics of 1 and 2 and determines the best split at each node. So overall, different components in this MapReduce implementation of decision tree is like this. So master will monitor everything and runs multiple MapReduce jobs. So besides master, there are three different type of MapReduce jobs which will be executed. So first is the initialization of MapReduce, that is, it will be run once. So for each attribute, it will identify the values to be considered for the split. So for example, the root node. So for the root node, decision has to be done during the initialization phase, and then it there will be a second set of MapReduce job to find out the best split, and it will run multiple times for each level. Of decision tree growth. So the second step will keep on increasing, keep on growing the levels of the tree as they are being invoked. So the number of times it is invoked, so that indicates that it will be growing in that levels. So that particular MapReduce job is to find the best split when there are too much of data to fit in the memory. So this way, this MapReduce will try to find out the best split and keep on splitting, and also it will be then the next step is finally the MapReduce will build the in-memory build, that is, subtrees are built at each MapReduce, then they will be runs once. So similar to find the best split for small data, it will grow an entire subtree once the data fits in the memory. So these three different MapReduce jobs, one is for the root node, that is the initialization, the second one is at the level wise splitting of the nodes and growing the decision tree, and finally it has to take these subtrees which are in memory and build during each runs. So it will be done once. These are the references for this discussion which we have just seen. Example: medical application using decision tree in Spark machine learning. Now we will consider an example of the medical application of the application of decision trees for using Spark MLlib. So in this example, we will see how the classification using the decision trees is done. So let us see the steps for doing this decision tree based analytics for the medical application. So here we are going to consider the medical application using decision trees for big data analytics. Now, here we have to see that we have to give the name of the application, and now we have to create the Spark context using this application name. So, we call it as the Spark context. We have to create a Spark context. After creating the Spark context, then we have to build a session that is called a Spark session. This is step number 1 and this is step number 2, which is essential in all such applications which runs under Spark. First we have to create the context, then a Spark session, and this is required to build the data frames. The next step would be to download the data set which is used here in this example. So, we will download the data set from some link, and let us call it as this data set which is being downloaded. Once the data set is available and is downloaded into the Spark system, then we have to see that this particular data set has 3 different parts, that is in the form of a key value pair. It has an ID number, and then it will have the key as whether it is having a medical problem, yes or no, means malign or having benign, and then different features of it. So, the data will be in this particular form. It will be a diagnosis, and then it will be a features. Now, this diagnosis, if it is M or B, it has to be converted into the numeric form. So, we have to convert, we have to load into file, and we have to convert this field into the numeric field. So, out of this particular data set, that is 569 examples in the data set, we have to convert in this particular field of diagnosis into the numeric values, and then we have to see this particular explore the data set. So, after having read this particular data set which we have downloaded, now it will be creating the data frames with the label and the feature, and the label will be converted into the numeric values, and after that this particular data set which will having these values converted into, so these M fields will be converted into the numeric values, and then now after converting it, now it will be ready. So, the conversion will be M is equivalent to 1 and B is equivalent to 0. So, wherever 1 is there, M is there, so it will be 1, and wherever B is there. So, after this conversion, now this particular data set will be now ready for the use of machine learning. So, the first after preparing the data, now we have to use the data for the machine learning. For that, we have to split this data into the training data set and the test data set into the proportion of 70 and 30. So, to split this data set into the training and test data splits, now we have to use this particular Spark command, random split, that is 70% is of training data and 30% is the test data. So, after this splitting of the training data and the test data, now we are going to apply this decision tree algorithm. So, we will now use the decision tree classifier, and now we will use this label indexed which we have seen in the previous slide, and then we will do this decision tree fit on the training data set which we have already obtained from the data set split 70% of it. So, after this step we are ready with the decision tree. Now, we can see out of this decision tree its different parameters, such as how many nodes are there in the decision tree, what is the depth of the decision tree, and also what are the features which are of importance, and this will build the model of a decision tree. So, decision tree model is being built here after this execution. Now, now we can see that if we find out how many in this particular data set of around 600 different samples, we have seen that there are 29 different nodes are there, and the number of depth is only 5, and different important features which we have obtained in the form of the graph, and number of features are 30. So, after constructing this particular decision tree, now we have to see that we have to evaluate this particular decision tree, whether it is the quality wise, whether it is good or bad, how it is good for the predictions. So, evaluation is done. So, multi-class classifier, multi-class classification evaluator is used for this particular purpose to evaluate the predictions accuracy. So, we want to evaluate the prediction accuracy, and by that by this particular method we have to see that the prediction accuracy which is calculated for this decision tree construction is around 96%, and this is fairly good which we have generated. Here we can see that these predictions are shown here in this case. So, this is the decision tree which is generated, which is nothing but here you can see all the predictions. That means predictions are there at the leaf nodes, and all other nodes are there, the decision nodes are there at the internal nodes. So, this is the prediction node, this is also the prediction nodes, this is also the prediction node, and you see that this is the decision tree which is being calculated out of the training data set, and using the test data set we can evaluate this particular model of a training of a decision tree which is being generated based on its prediction accuracy, and we have seen that the prediction accuracy comes out to be 96%, which is fairly well. So, conclusion in this lecture, we have discussed the decision trees for big data analytics, and we have also seen one case study of a medical application wherein we have applied the decision tree based on machine learning, Spark machine learning. Thank you.